Okay, the third talk in the session is going to be given by Zilong Wang. He's a PhD student at the Hong Kong University of Science and Technology, where he's advised by Kai Shen. And his research interests are in data center networking and hardware acceleration. And he's recently been focused on high-speed networking and networking for AI. And he's going to talk to us about fast, scalable, and accurate rate limiting for RDMA NICs.
Okay, thank you for the introduction. Hi, I'm Zilong Wang from HKUST. Today, I will present our recent work title, a fast, scalable, and accurate rate limiter for RDMA NICs. This is a joint work with ByteDance. We first introduce what's the rate limiter, why we need it, and how it works. There are some policies in RDMA NICs like congestion control and traffic isolation. The congestion control precisely allocate the bandwidth across floors and help mitigate the network congestion in high-speed networks. And traffic isolation, required by practical cloud management, will sense rate to VM pairs to ensure stable application performance and user experience. These policies output rate limits for each floor like 100 Gbps for floor 1, 10 Gbps for floor 2, and then ask the rate limiter to enforce these policies. Specifically, the rate limiter does two things. First, rate limit. It enforces a specific rate on each floor. Second, pacing. It injects inter-packet gaps to smooth the traffic. Then the rate limiter runs in the data path of the RDMA NICs, determining which floor of QPL's head packet to transmit next and when to transmit. The rate limiter first computes the transmission time of the packets among various floors. Then it sorts all packets based on the transmission time and transmit it on time. Then we discuss the desired properties of the rate limiter. First, in the host, rate limiting requires the rate limiter to be accurate and scalable. For high accuracy means the rate limiter should precisely enforce the given rate on each floor and inject inter-packet gaps to smooth the traffic and preventing the traffic burst. Inaccurate rate limiting could result in traffic burst and worsen the network congestion. Also, the rate limiter should support a wide range of rate limits, like from 100 kbps to 100 Gbps, and allow for fine-grained adjustment instead of some fixed values. In terms of scalability, high scalability means the rate limiter must support rate limiting for tens of thousands of floors at the end host. Since the memory and computing resources are limited in hardware, the RDMA NICs desire a scalable rate limiter that could support many floors with low hardware resource consumption. Besides accuracy and scalability, RDMA NICs desire the rate limiter to be very fast. RDMA NICs or NICs which offloads the RDMA protocol are known for their ultra-high performance. For example, the NIC can achieve a high packet rate of 110 million packets per second, transmitting a packet every 9 nanoseconds. When NICs deploy the rate limiter when NICs deploy the rate limiter lies in the data path of the NIC because the rate limiter is responsible for the packet transmission. So the rate limiter's performance directly impacts the performance of NICs. If the rate limiter runs slowly, it will reduce NIC's throughput or packet rate. Also, a higher packet rate helps it to saturate a higher link bandwidth, like, for example, 400 Gbps. So the rate limiter should operate fast and achieve a high packet rate, like transmitting a packet every 8 nanoseconds. However, existing works fail to meet all these requirements. We first discuss a typical commercial NIC Bluefield 3. We observe a performance anomaly when enabling the rate limiting for more than 10,000 floors. As shown in the figure, we observe up to 13% throughput degradation when enabling the rate limiting for like 16,000 floors. We use the programmable congestion control framework to test the rate limiter, and the detailed setup can be found in our paper. This performance anomaly indicates some potential performance issues with its rate limiter, though it is a black box and hinders further analysis. On the other hand, recent studies, Scenic and Pyle, design accurate and scalable rate limiters for end-hold SNCs. However, they are not fast enough. As shown in the first figure, it achieves only 13% throughput and packet rate compared to RNIC when supporting 16,000 flows. When giving a higher mic capacity, like for example 400 gigabps, as shown in the second figure, this low packet rate makes it insufficient to saturate the link bandwidth. To figure out the performance bottleneck, we then analyzed the workflow of Scenic file and found that they follow a monolithic design. Specifically, the first sorts all flows and schedules the nearest one to be sent. Once the flow is scheduled, it fetches and transmits its head packet. Such flow level rate limiting is accurate and scalable, but slow, because it transmits only one packet after sorting all flows. And sorting many flows is slow and becomes the performance bottleneck. Sorting many elements quickly in hardware is inherently challenging. The reason is that the increased number of flows to be sorted will increase the complexity of hardware combinational circuit, then decrease the maximum achievable clock frequency of the sorting circuit as well as the sorting rate. This is because the sorting rate is the clock frequency divided by the cycles per sorting operation. For example, with 200 million clock frequency and 2 cycles per sorting operation, we got 100 million packets per second. The figure here shows the maximum clock frequency achieved by Scenic and Pyle decreases with the increasing number of supported flows, which causes Scenic's and Pyle's low performance. Instead of tackling the challenges of sorting, maybe we can rethink the workflow to improve the performance. We noticed that the workflow of previous monolithic rate limiting consists of 2 steps: flow scheduling and packet transmission. Thereinto, flow scheduling seeks scalability and packet transmission seeks accuracy and performance. So this provides a chance to renovate the workflow and design a hierarchical rate limiter that meets demands separately. Here is the idea. We first inherit the scalable flow level rate limiting to sort tens of thousands of flows and schedule the nearest one. Once a flow is scheduled, we fetch multiple packets. Then, we additionally apply accurate and fast packet level rate limiting to this batch of fetched packets. We filter packets close to be sent and drop to the left. This helps us to reduce the number of packets to be sorted. Finally, we sort these a few hundreds of packets and transmit it on time. Based on this idea, we designed Tensor. Tensor's design goal is to improve the performance while maintaining accuracy and scalability. To achieve this goal, we follow these 3 design principles. First, enable the transmission of multiple packets after sorting all flows to improve the packet rate. Second, utilize the time-based rate limiting algorithm and transmit precisely based on the calculated timestamps, ensuring accuracy. Third, save memory and computing resources in hardware as much as possible by avoiding unnecessary buffering or too complicated data structures. Guided by these design principles, Tensor designs a 2-tier hierarchical rate limiting by first applying scalable flow level rate limiting, followed by fast and accurate packet level rate limiting. We then integrate Tensor into RNIC's architecture by replacing the original QP scheduler module. As shown in this figure, Tensor's hierarchical design consists of the flow level rate limiting and packet level rate limiting. And here is the workflow. First, sort flows. The flow scheduler first sort tens of thousands of flows by their head packet transmission time, and then identifies the latest flow. Second, monitor and schedule. The flow scheduler monitors the current system time and schedules the latest flow on time. Next, fetch packets. The flow scheduler fetches multiple packets for the subsequent packet level rate limiting. Then, compute transmission time. After fetching the packets, the time calculator computes the packet transmission interval and the packet transmission time based on the packet size and the rate limits. Next, filter imminent packets. From fetched packets, the packet filter picks imminent packets that are close to be sent. The rest of the packets are dropped and refetched next time. Next, reschedule. The packet scheduler notifies the flow scheduler to update the head packet transmission time and reschedule it for next time. Next, sort packets. The packet scheduler then sorts these imminent packets based on their transmission time, and at last, monitor and transmit. The packet scheduler monitors the current system time and transmits the nearest packet on time. We then introduce how to integrate Tessor into RNIC's architecture. The figure shows a typical RNIC architecture consisting of 4 parts. First, QP scheduler schedules QP. Second, DMA engines fetches rookies and data from the host. Third, the transport implements the RDMA transport protocol and generates the packet header for when the payload arrives. And at last, the basic NIC sends and receives the packet from the network via the MAC interface. We integrate Tessor into RNIC by replacing the original QP scheduler module. There are 6 sub-modules. Emacs gathers all scheduling-related events, like doorbells, and maintains a list of active QPs. The QP scheduler then uses the timeline module to sort QPs, and uses the timer to monitor schedule the QP on time, and then fetches rookies and store in the rookie buffer. The packet scheduler processes these fetched rookies, computes the transmission time for the packets in these rookies, filters the imminent packets, and sorts them in the timeline module. And at last, the timer notifies the packet scheduler to consume rookies and transmit the packets. The timeline module is the core of Tessor. It sorts QPs and packets. There are various stages with different requirements. For example, QP scheduling desires high scalability and medium performance, while the packet rank sorting desires low scalability but high performance. So Tessor chooses the suitable data structure for each stage and uses the combination of data structures to collectively meet the requirements for accuracy, scalability, and performance. These dedicated data structures include pipeline heap, timing wheel, and register error. In summary, Tessor is fast as it enables multiple packet per sorting transmission, improving the packet rate. Now the maximum rate has increased from sorting a few thousands of flows to sorting a few hundreds of packets. For scalability, Tessor is resource efficient and achieves high scalability. No packets are stored in hardware, and only a few rookies are stored, about 500 bytes for all QPs. In terms of accuracy, Tessor can transmit packets precisely based on the calculated transmission time, and can enforce the rate limit and prevent the traffic burst. We implement the prototype of Tessor using Intel FPGA, running a clock frequency of 250 million Hz. We realize 16,000 QPs in Tessor, and the resource consumption is broken down in the table. The resource consumption of Tessor is considerably low, and it can achieve high clock frequency, and this makes it friendly to get integrated into various architectures. For the evaluation part, we first show that Tessor can achieve a high packet rate. We measure the aggregate throughput of multiple flows while increasing the message size. As shown in the first figure, Tessor can achieve 125 million packets per second, which is 3.6 times higher than silicon pile. We then measure the maximum clock frequency that the rate limiter can achieve, varying the number of supported floors. As shown in the second figure, Tesla achieves a high clock frequency and shows a slower decline in frequency when the number of floors increase. We also compare Tesla with Bluefield 3 in terms of the aggregate throughput while increasing the number of QPs. As shown in the third figure, Tesla consistently maintains a high throughput without performance anomaly. Meanwhile, Tesla achieves high scalability. As shown in the figures, Tesla shows very low resource usage. Even when supporting 16,000 floors, the computing resources used is less than 5% of our FPGA, while the memory resource is less than 1%. In comparison, Scenic and Pile consume 3 to 13 times more resources under 16,000 floors. In addition, Tesla achieves high accuracy. We evaluate Tesla's accuracy by configuring rate limits ranging from 100 kbps to 100 gigabps for a single floor, and as shown in the first figure, Tesla accurately enforces the rate limits for any given configured rate. And we measure the Bluefield 3 achieves like 400 kbps when sending a rate limit of 200 kbps. We then demonstrate Tesla can precisely enforce configured rate limits for tens of thousands of concurrent floors. And as shown in the second figure, Tesla's accurate rate limiting enables each floor to achieve the configured rate limits precisely. And when the aggregate rate limits exceed the link rate, Tesla can proportionally adjust the flow rate. As shown in the third figure, when the aggregate rate is 200 gigabps, which is twice the link rate, the rate achieved by each floor is just half of the configured rate. To summary, we present the design and implementation of Tesla, a fast, scalable, and accurate rate limiter for RDMA NICs. Tesla's hierarchical rate limiting combines scalable floor-level rate limiting with fast and accurate packet-level rate limiting. With Tesla, our NIC now can precisely allocate bandwidth resources at end host, and we hope this can inspire more innovative protocols in high-speed networks or domain-specific networks aiming at a congestion-free data center. For example, AI training clusters can leverage the predictability of the training workload to assign the sending rate between GPU pairs to avoid the link congestion. Okay, thank you for listening.
Question?
Very good talk. I have two questions. One is that when you mentioned that in your scheduler there is something like time window, and if the packet do not in the nearby time window, you will drop it. What do you mean you drop it? Is it need to retransmit on the sender side or something else?
Actually, the workflow is that we fetch multiple wikis, and like 4 wikis, and we picked, and we found the first 3 wikis are close to be sent, and we drop the first wikis in the sender in the RNIC and update the send pointer to like 3 instead of 4. So next time when we reschedule this QP, we will fetch this wiki from the, we will refresh this wiki, and no package retransmission will happen.
Okay, the data is still here, right?
We don't touch the data.
Okay. The second question is that you implement it in the FPGA, right? And you have a comparison with the Teco and the Bluefield rate limiter. Is this the rate limiter in the Bluefield alternative to Teco, or can you improve the rate limiter implemented in Bluefield 3?
Okay, Bluefield 3 is a commercial NIC. It is an off-the-shelf product and is a black box. We found there are some potential performance issues within the Bluetooth rate limiter, and we propose a new design which can be used in different RDMA NIC architectures.
Okay. Is there any possibility to leverage your idea to the black box DPU? I mean, don't touch the transport layer.
Oh, sure. Actually, we are the rate limiter, and we also are the scheduler. So it's more related to the DMA layer instead of the transport layer. So we can replace or improve the original rate limiter or qubit scheduler to fix its issue or improve the scheduling rate or something about rate limiting. And we will not touch the transport layer.
Okay, thank you.
All right, thank you for the questions. But we're going to have to move on, so let's thank the speaker again.